Let's take a look into the relationship between potential energy and conservative force. Well, this might seem a little non sequitur, but consider a value x. And we take x and then we square it. And we take the square root of that. We're back to the original value, x. Let's take the same value, x, and take the cosine of that. And then let's take, the inverse cosine of the cosine of x. Of course, we're back to x. Take a value x. Take the natural log of that value. Take e raised to the natural log of x, and we're back to x. Take 2 steps forward. Take 2 steps back. You're back to where you started. Anyway, we understand what a lot of opposite operations are. We defined earlier that work is equal to the integral of f dot ds. And we've also stated in this unit of study that the work done by a conservative force is equal to negative the change in potential energy. So in other words, change in potential energy is equal to negative the integral of f dot ds. Well, the reason for all this nonsense, I want to ask the question, what's the opposite of squaring something? Taking the square root. What's the opposite of taking the natural log of a value? That's raising e to some value. What's the opposite of walking to the right? Walking to the left. What's the opposite of integration? Taking the derivative. So it should stand to reason, if this statement is true, then shouldn't it be true that force is equal to the negative of the derivative of potential energy with respect to position? That's the topic of study for the remainder of this unit, the relationship between force and potential energy. So let's illustrate this with the ideal spring. If we were to take the spring and pull it to the right, stretching the spring by some displacement delta x, along the way, if we establish the relaxed length of the spring as the position of equilibrium where x is equal to 0, then whatever the position of the block x, the force at that instant is equal to negative kx. The reason for the negative sign, the force exerted by the spring would pull to the left even though the displacement was to the right, and vice versa. If we were to compress the spring, then the displacement would be to the left, but the force would be to the right. This is known as Hooke's law. The potential energy in the spring is equal to 1/2 kx squared. So it doesn't matter whether the spring is stretched or compressed, as long as it's compressed the same distance that it's stretched, it should have the same amount of potential energy stored. Whether x is positive or negative, potential energy is going to be positive. So what I'd like to do is make a graph of potential energy versus the amount of stretch or compression. So we'll put the potential energy as a function of x on the y-axis, and we'll put the displacement along the x-axis. So if we were to stretch it to the right, the potential energy gets greater and greater and greater, and it's nonlinear. We can see that the potential energy is proportional not to x to the first power, but to x squared. And likewise, if we compress, we also get an increase in potential energy. So this is basically just a parabola, right? So what do I mean when I say force is equal to negative du dx? Well, derivative is the same thing as slope. So what we're saying is the force isn't the slope of the graph. We're saying the force is the negative of the slope of the graph. So for example, when the spring is at a position x, as indicated in this dot, then the amount of potential energy is, of course, some positive value. But what about the force? The force is the negative of the slope. So at this point, the slope is found by taking the slope of a tangent line. Well, that slope is definitely a positive value, which means the force would be a negative value. Likewise, if we compress the spring instead of stretch it, maybe to this position x, then again, the potential energy is positive. Now let's look at the slope of the graph. The slope at this point is negative. So what's that tell us about the force? That means the force must be positive. The force is the negative of the derivative of potential energy with respect to x, which means the force is the negative of the slope. So what does that imply about this point right here? Well, at that point, the slope of a tangent line is equal to 0, which means the net force is equal to 0, which means that is the point of equilibrium. But of course, we know that this is the only position at which the acceleration of the mass attached to the spring would be equal to 0. This position of equilibrium can be labeled as one of two types: either stable equilibrium or, you guessed it, unstable equilibrium. Well, let's say we had a different system, not a straightforward mass attached to a spring on a frictionless surface. I'm going to give you a hypothetical graph of potential energy versus displacement. What if that graph looked something like this? Are there any points of equilibrium that you can identify? I would hope so. Basically, for equilibrium, we know from our first unit of study, when net force is equal to 0, acceleration is equal to 0, and we say an object is in a state of equilibrium. Force is equal to the negative of the slope of potential energy with respect to position. So as long as the slope of the graph is equal to 0, then the force must be equal to 0. So the points of equilibrium are here and here. And I want to show you that this represents stable equilibrium, and this point represents unstable equilibrium. And that's pretty easy to do. Imagine whatever this graph represents. If we were to take the object, and there it is at its position of stable equilibrium, and we displace it a little bit to the right. So think about that. An object that's totally stable, and you nudge it, you give it a little push off to the right. Well, then that puts us at this location. And at that point, the slope of the graph would be positive. But remember, if the slope is positive, that means the force is negative. Well, what would it mean for there to be a negative force on the object? That means it would be pushed in the negative direction. So we nudged it to the right to take it out of equilibrium, and as a response, a force naturally showed up on it that pushes it back to the left. If we took that same object and it starts out at this position of stable equilibrium and we give it a nudge to the left, then that puts it at a position here where the slope of the graph would be negative, which means the force would be positive, which means it would get pushed back toward the equilibrium position. So see what I mean? This must be a point of stable equilibrium, because any attempt to displace it either to the right or to the left would result in a force that pushes it back toward that equilibrium position. Now, if the object was located at this point and we gave it a little nudge to the right, then it would end up at this position where the slope of the graph is negative. And if the slope is negative, that means the force is positive. So we already displaced it a little bit to the right to take it out of this equilibrium, and then a force shows up that pushes it even more to the right. That's definitely a point of unstable equilibrium. So there's an introduction to this relationship between potential energy and force. The relationship is simply that force is equal to the negative of the derivative of potential energy with respect to position. Much of our study on this topic is going to be an investigation of graphs of the potential energy with respect to position versus the position. So thanks for watching, and stay tuned for more.